Welcome to the flock. Let's dive into using the ideal gas law equation to solve for pressure, volume, moles of a gas, and temperature. Stick around to see how problems like these are solved. When we combine Boyle's law, Charles' law, and Avogadro's law, including the gas law constant, we end up with the ideal gas law. So essentially what we've done is tie all of the gas laws together to create an equation that looks like this. PV equals nRT. Now remember that P stands for pressure, V stands for volume, N stands for moles, R is the universal gas constant, and T stands for temperature in Kelvin. So if we're going to use PV equals nRT, we first need to read our question and figure out which variable goes in which spot. The first hot air balloon was used by Charles in a historic flight in 1783, and it was filled with about 1,300 moles of hydrogen gas. Now mind you, hydrogen gas is really flammable, so Charles is really lucky that he didn't encounter a spark anywhere in this hot air balloon voyage. So first thing you should know is that we have a mole value. That's our N. What's the rest of the question say? If the outside temperature was 21 degrees Celsius, that's our temperature, but we still need to convert it to Kelvin, and the atmospheric pressure was 750 millimeters of mercury, there's our pressure, what was the volume of the balloon? So we're solving for V in this case. So hopefully right off the bat, you're noticing that we have N, we have T, we have P, we're solving for V, but what is this R thing? What are we gonna plug in for R? We can only have one missing variable in order to solve an equation like this. We have many different numbers for R. The two R's that you should know off the top of your head are 8.314 liters times kilopascals divided by Kelvin times moles, or 0.0821 liters times atmospheres divided by Kelvin times moles. Notice that the only difference between these two universal gas constant R values are the units of pressure, and that's what also happens to change the number itself. The pressure we have here is in millimeters of mercury. So from the two R values that we remember, neither of those match millimeters of mercury. Now all of our units need to match before we can plug it into an equation. That means we're going to need to convert the millimeters of mercury here to either kilopascals or atmospheres of pressure in order to use one of these R variables. All right, so I'm going to make an executive decision here, and we're going to try and convert this millimeters of mercury into atmospheres instead, so that we can use this R value in our equation. Anytime we do a conversion, of course, we're going to start with our given as the first thing on our magical line to freedom. And we're going to put our goal at the end of that line. In this case, our goal is going to be atmospheres of pressure instead of millimeters of mercury. We know that in 1 atmosphere of pressure, we have 760 millimeters of mercury. So essentially, all I have to do is multiply 750 by 1 and divide that by 760. And I end up with an atmospheric pressure of 0.987 since I rounded up. That value is now going to take the place of the 750 millimeters of mercury that I would have originally used. This way, all of my units will match when I plug it into the ideal gas law. Now all we have to do is plug and chug into the ideal gas law equation. My pressure is the 0.987 atmospheres that we just converted from the millimeters of mercury. My V is my X variable, what I'm trying to solve for. And we're setting that equal to the moles of the gas present, which is 1,300 moles of hydrogen gas. We're going to multiply that by the R value that matches our pressure value. So we're going to use this R value up here, the one that has ATM in the units. So that's going to be 0.0821 liters times ATM divided by Kelvin times mole. And then we're going to multiply that by the temperature in Kelvin. So first we have to add our 21 degrees Celsius plus 273 to convert it to Kelvin for a temperature value of 294 Kelvin. Before we do any math here, I want you to see how all the units will cancel and leave us with the units of what we're solving for, i.e. our volume. So we should be left with liters. Notice here that the moles will cancel here and here, and the Kelvin value will cancel here and here. Let's hold off on the other units for a second. We'll multiply our 1,300 by 0.0821 and multiply that by 294. And that gives us an answer of 31,378.62 in units of liters times atmospheres. Now, as in any other time in math, when we want to get a variable alone, we're going to need to divide off the number. So to get x alone, we're going to divide both sides by 0.987 ATMs. And now we can clearly see that the ATM unit also cancels, and all we're left with is liters. That's exactly what we wanted since we're solving for volume after all. So now all we have to do is take 31,378.62 and divide that by 0.987. So our final answer is 31,791.91 liters of gas in that hydrogen gas balloon. So the great thing about this gas law equation is that if you're just missing one of the variables, either pressure, volume, moles, or temperature, you can solve for that one variable. Keep in mind that your R is assumed to be in your head. They're likely never going to give you that R value. They're assuming you remember that it's 0.0821 atmospheres or 8.314 kilopascals units. Now that you've seen me solve one, go ahead and give this one a try. Pause the video now. Let's check your answer. And there you have it. You should have gotten 19.89 liters. Now, before we try solving for pressure, moles, and temperature using the same ideal gas law equation, let's speed through how we can rearrange PV equals nRT to solve for one of the variables, if you're uncomfortable moving the numbers around after the fact. Let's start with pressure. Next up, volume. Let's solve for moles next. And lastly, let's solve for temperature. Now you have the equation set up to solve for any of the variables that you might be asked to solve for. So using that knowledge, let's solve for temperature. Go ahead and pause the video here and see if you can solve it before I show you the answer. Let's see if you got the right answer. Alright, you should have gotten a very hot temperature of 1,329.67 degrees Celsius. Hopefully you're recognizing that the whole premise of this ideal gas law equation is all about units. I'm not drawing out the units every single time because it's fun. I'm doing it to make sure that all of my units do in fact cancel. In this case, volume has to be in liters. So if the problem would have given us milliliters, for example, it would not have canceled with the liter value that's in the R units. So you have to make sure that all of the units in your pressure, volume, moles, and temperature will match the units that are in your R value. Otherwise, this whole thing will not work. And it's often used as a trick question for a lot of chemistry teachers. Just an FYI. Let me show you what this ideal gas law equation looks like with a PhET simulator before we solve for the moles and the pressure next. So with this simulator, we can see how changing the pressure, volume, temperature, or amount of moles of a gas will affect all the other variables in the system. So let's first add some heavy molecules of gas to the system by pumping them into the container. Notice that as I did so, the pressure started to rise. We went from zero pressure to now around 40.8 ATMs, atmospheres, and the temperature also rose. What happens if I expand the volume? Well, if I make the container bigger, the pressure goes down and the temperature stayed the same. As they move faster because they're hotter, now at 1008 Kelvin, they collide with the walls of the container more often due to that increased kinetic energy, and that causes the pressure to rise now as well to 91.7 atmospheres. Let's cool this whole system back down. We'll bring it all the way back down. Whew! Now they're barely moving and the pressure dropped substantially lower than what we started with. But if we decrease the volume again, this should increase the pressure, even though it's really cold. Notice that the pressure did in fact go up. We can also increase the pressure by adding more gas molecules. Just like if you were pumping up a bicycle tire. We can release this pressure by releasing some of the gas molecules, just like if you had a hole in your car tire or your bicycle tire. The same kind of concept happens with lighter or smaller molecules of gas, but they just happen to move faster from the get-go. And because they move faster from the get-go, they're going to collide with the walls of their container faster and cause more pressure. Now let's get back to solving some gas law equations. This time we're going to solve for the moles of a gas. Go ahead and pause the video here and see if you can get the answer before I show you how to do it. Let's check your answer. Here you should have gotten 0.005 moles of the gas. Notice that here we had to use an R value that had kPa in it instead of our 0.0821 atm R value. That's because the pressure we were given was in kilopascals, so we need to use an R value that matches that pressure value. And last but not least, let's solve for pressure using the ideal gas law. See if you can solve this one yourself. Pause the video now. Did you get it right? Let's find out. So in this problem, it was a perfect example of how you could use either R value that you've memorized. You're just going to end up with a pressure that is either in kilopascals or in atmospheres. It didn't specify what they wanted the units of pressure to be in here, so it doesn't matter, you pick one. Now that we've been through Boyle's law, Charles' law, Avogadro's law, the combined gas law, and now the ideal gas law, you should be able to pick out which gas law you need to use based off of what a question's asking for. Make sure that you test yourself by trying these questions out, both the ideal gas law questions at the top where the answers are given in red, and the mixed gas laws to make sure that you can identify which gas law you should use. In this lesson, we talked about the ideal gas law, which basically smashes together all of the gas law equations so that we have pressure, volume, moles, temperature, and the universal gas constant all in one beautiful equation. We rearranged PV equals nRT in order to solve for each one of those variables independently, in case plugging and chugging and then solving thereafter isn't your thing. We then solved for each one of those variables, pressure, volume, temperature, and moles, using our universal gas constants that match the units within the equation. Always make sure your temperature is in units of Kelvin, and make sure that your volumes are in liters. Make sure that your pressures match between the pressure given and your R value used. Please give this video a quacks up and subscribe to Duckonta for some free educational content. Quack you later.
No ducks, no glory.